APIs, semi-permeable osmotic interfaces. So just as a summary, APIs can be modeled using the metaphor of semi-permeable interaction boundaries between the intended high-fidelity human-centered interfaces, which is where I operate a lot of the times, but it goes all the way through the stack, and how that is interpreted into a coded implementation. So moving beyond redlining static images, literally putting messages on static pictures, I'm going to discuss approaches and recommendations to consider, your human developers and operators' experiences with APIs, looking at user interfaces. So here's a summary. I was listening to a talk by, I've forgotten the guy's name now, and he said, always enumerate what you're going to talk about so people know how long you're going to torture them for. So I'm going to have an introduction, definitions, metaphor for the API space, and then an example that I've worked on recently where I've used this approach, and then leave time for questions and answers. So hi, this is me. Take a screenshot or share this later. So I'm a computational designer, as Lara said. We're creative people applying our mastery and knowledge of how people work, software, hardware, data, networks, and systems all interact in one closed system while they're operating in an open system environment. So I work as a design principal in IBM, and what I'm doing is helping clients with business partners to simplify their IT management and operations, using preventative maintenance, analytics, and deep learning probabilistic insights. So a couple of things I want to do, first of all, is just go through some definitions, because I'm going to use these later on. So what is a application programming interface, or affectionately known as an API? It's a mechanism for two or more computer software programs to connect, communicate, transport, transfer, transform the transported objects to create a function capable of doing some work. APIs are usually specified individually or atomically without necessarily suggesting their sequencing and dependencies. And this is one of the pain points you have if you're trying to consume and use these. What's a semi-permeable membrane? It's a biological or synthetic layer that allows only certain molecules, think of them as objects, to pass through them. What is osmosis? It's the process where the molecules of liquid or objects pass through that semi-permeable membrane, usually from somewhere that is less concentrated to somewhere that is higher concentrated. And this is a really quick image of what it would look like. So if you had a mixture with the purple dots are some kind of substance, the white dots are water, and then you put a semi-permeable membrane in between the two of them, what's going to happen counterintuitively is that the water is going to move from the area of low concentration to the area of high concentration to even out the balance of the system. The first time I actually saw this in a lab, it looked like magic, but it's explainable, and it's a metaphor I'm going to use later on when I talk about APIs. Last thing, second to last thing that I'm going to define, cognitive dissonance is a psychological term describing the mental conflict that we experience that occurs when a person holds two beliefs that contradict each other. Now, some perspectives may contradict each other when they are flattened in planar orientations, when in fact really there's a spectrum of possibilities in the same space. So hot is the opposite of cold. Something can be cold and hot at the same time, depending on where you're measuring. Last thing I'm going to talk about, define, is assumptions. Is a statement or a thing that is accepted as true or certain of occurring without proof. I'm personally on a mission and would recommend that we use presumptions instead, which is a statement or a thing that's still accepted as true or certain, but on the basis of probability. The nature of probability is that it takes into account all the variables that are acting at that point in time when the probability of occurrence is assessed. So it allows things to be changeable over time rather than accepting you've made an assumption without any proof and you have no idea if it's valid. So metaphors for API space. I think about APIs occupying a three-dimensional space, but the way we talk about them is as if they're in two dimensions. Favorite quote of mine is, "The things you tend to dismiss as mistakes, perhaps you should take more seriously. They weren't what you intended, but that doesn't mean that they're wrong. Or complexity, maybe they're just complicated." So talking about metaphors, and I've already mentioned earlier, think about and model each challenge that you're solving as a flattened three-dimensional space. Each flattened section is a semi-permeable membrane that only allows certain molecule objects to pass through it. So here's a quick animation. Once it starts, there you go. You got your three-dimensional cube, and then it actually flattens into a number of orientations and sides, but there are 6 sides for it. So the first one I'm calling complicated. The term actually means that it consists of many interconnected parts and elements. Complicated is also past tense, which assumes that we know what those parts are and how they all fit together. So they're known. The unknown unknowns are accounted for by stated or validated assumptions or presumptions. Planar or plane areas. From mathematics, a plane is a flat two-dimensional surface that can extend to infinity. And this is a lot of times how we look at and we address problems that we're looking at for APIs. A boundary from mathematics is the limits of a planar area or dividing line. And a dimension from mathematics and physics, again, is a minimum number of coordinates required to specify a point within that space. Complexity, again, from mathematics, it involves numbers that have a real known part and an imaginary unknown part. And interfaces are a point where 2 or more systems, organisms, organizations, or people meet to interact. So the interesting thing about all of this is that I've shown you one orientation of flattening a 3D cube. It could also look like this. So the same set of square units could be unfolded in a different valid number of ways, and it gives you the same result from a 3D perspective, but in 2D, the area and the length and the breadth and the ways that we'd measure it, it looks very different. So which one you use depends on which category is important for your purpose. So let's look at a real example that I've been working on recently. So if you're a designer using any kind of design tools, then this will be very familiar with you. Every screen, interaction, whatever you're designing is on a planar 2D surface, even though the space that you're modeling is a 3D space. Usually, we would use a practice we call redlining on the static screens to indicate interactions, connections, transfer dimensions with other systems, basically APIs. This is what it looks like, just mapping out all the interactions and pathways that a user would traverse in order to be able to use this application. And this only covers everything working perfectly. There are no exceptions noted here. The other challenge is that then we would need to insert all the APIs or calls to the other systems to support all the functions on each of these screens. So a system that we've kind of put together with my colleagues and also inspired by another gentleman called Brad Frost, we've called sort of interface membrane layers. And the idea behind this is because it's a membrane and it's a semi-permeable membrane, it's only going to allow certain molecules or certain objects to traverse between them. So here's an overview picture of them. Hopefully people are familiar with the atomic design system from Brad Frost. And we've modified it slightly to add particles, and already you can see that they are three-dimensional. So there are interactions and layers and membranes between those particles. You have atoms, which most people are familiar with, which is the buttons, the drop downs, all the things that you normally see on the screen. And then you start to combine them into allowed combinations to give you molecules. So for example, I'll now show an example of this a little bit later rather than describe it. Those molecules are then combined to give you compounds, and then compounds give you organisms, and all of these are filtered through templates to be placed on pages. So looking at this three-dimensionally, it would be represented by a number of facets, if you like. And this now gives you a vocabulary to show which API is used where, for what, when, and how, and what's the outcome and the result visually, as opposed to having to write a whole bunch of documentation that no one's going to read. So let's take you through an example and a scenario that would use this approach. So we're going to start all the way from the content model, which has been retrieved from another system, and take you through what this process or these interactions would look like. So we've got the content layer, which gives you your data and your state, and that's usually supplied from, guess what? An API, a database, a service, or something somewhere else. And then that is supplied to in a particular form. So you can see from the slide here, and this is actually a real item, I've got a date in epoch format and a few other pieces of data. We're going to be looking at how that date becomes human readable running through these semi-permeable membranes. So if there was an issue with that set of data or object, then it will be handled at the content model rather than be pushed forward. And the validation and everything else happens there. Otherwise, it doesn't go through. If it's not the right format, it doesn't go through that membrane. So next thing that happens, the content controller is something that will do a lot of the logic and functionality, looks at that data, and based on the requirement, that date needs to be transformed into English in a particular format. So that's applied at that layer. If it's not successful, so if it receives a number which is an epoch time, then the membrane will stop that from going through and handle that issue and that exception at that point, rather than let it percolate all the way through. So we've now got our formatted date in English with the month, the day, and the year. And we're now going to pass this to the view model layer, API, or membrane, which is going to receive that formatted information and then add some styling and some other requirements to it. So if you look at the bottom there, you'll see that it's taken the transformed and formatted date, added the type and a few other things, and then it's going to store it at that level for it to be reused again. So even though the source of the data was 3 layers back, we now have a model and a store that would be relevant, prepared, validated, used for this interface, which is the user interface, rather than having to go all the way back to the source of the data and rely on that. So now we've got our content, it's been validated, it's been formatted, and now it's ready to be packaged for presentation. So we're going to take it through to the particle layer. And the first thing the particle layer is going to do is it's going to take that date that has already been transformed and formatted and place it somewhere on the planar layer, which is the screen. And this screen, really, the way that I think about the screen is really, it's a 3-dimensional because it has layers, it's got opacity, it's got a whole bunch of things, styling that will be exercised even though we're just looking at this on the screen. So you've got the date, you've got the place, and then there's some kind of decoration that's going to happen in the view particle layer. And again, if that's not successful, then it'll be handled there, and the right interactions for exception handling would then take place, rather than displaying this to a user who can't do anything about those things. So we're now moving into composing that information into an atom, and the view, the styling and interaction layer will take care of that. So now we've got views, which are atomic components. We've got nested views, which are molecular components, which are made up of atomic components. And we've now got things like primary and secondary buttons. So you have a button, and then you're able to specialize it. You have checkboxes, the same thing. Text boxes, text areas, text strings. These are all to do with text, but they're specialized for a particular function. And again, all of that is assembled in the view. So you've got the example at the bottom where you've got the date, you've got the place, you've got the decoration and the styling, and that all composes to give you a text box on a screen on a layer somewhere. Then we've got the composition, where we're now taking those items almost like Lego building blocks, moving them around and keeping them together to be able to display on the screen. Now remember that this is percolated through about 4 or 5 different membranes, allowing only certain objects to pass through. So that would look like that. So we've got component, which is a space and a panel. And then we've got another component, which is a graph. The two placed together give you a molecule, which is made up of the background, the foreground with the graphics, and some description and layers. So this is now starting to compose things together. The final layer, then, as we go through, is the composite, which starts to plug these things, these molecules together to be things that are reusable, formatted in a particular way. So some of the examples that I've got here are a background panel with 2 charts on them The charts are the atoms put on the background panel with descriptive text, which is another atom, all combined in a certain way that would be consistent and responsive as well. And all of these building blocks, they're pretty much now like Lego blocks. They're composites, so we can mix and match them. Now have to go through one more filter or membrane, which is the template. So you basically throw these things at this template, and they don't pass through if they don't match or they don't have a place to go. And so there's a whole contract that is written into the template to say, I'm expecting this sort of composite to show up here. I'm expecting this sort of atom to show up here. I'm expecting this sort of molecule to be placed in this location. So even though we have flattened this 3D space, it's still all specified by the API with all the multiple uses. The final thing then that happens is it composes to give you a bunch of wonderful pages that should hopefully be error-free, functional, what you ask for as a user, and you can go ahead and interact with. And if there is an exception, then those will have components and interactions that would take care of that. So one other thing that I would say about membrane layers are that what I've been talking about, and this is actually a real example, has been operating at least 5 levels above a whole bunch of systems below it. So the example that I expanded on was the presentation layer with extended capabilities. This is used to assemble a variety of different applications and functions that are then used by a business to provide value to their users. Below these, we've got other systems that supply to the content model, for example, a building semantic model. It could be any other kind of model, analytics, machine learning, which is all the rage and de rigueur today. Below that, we tend to have an Internet of Things connection service, which goes and collects and aggregates information from sensors and a number of different devices. Below that, we've got a gateway, connectivity layer, which is aggregating all of that information from various places. And you can see that the top part is in the cloud, and it's a software as a service. The bottom part is in a bunch of individual buildings. So each building that has a number of sensors installed, and they are measuring things like temperature, humidity, noise, even dust, variable compounds, is all then sent and aggregated to this service, and then that is used and split into a number of perspectives, again, membranes, and these are then passed to the content model, to the controller, up through the view model, that creates particles, which are then able to be displayed, assembled, put together, and finally put on a page, and then multiple pages give you your application. And if you remember that diagram that I showed earlier with all of those interconnections, is a 3D space with all of those interactions and handling exceptions also as well. So just a reminder, all of that stuff that has been flattened gives you your 3D space, which is a cube. Each side of the cube is a number of different semi-permeable membranes, APIs, which allow certain molecules only to pass through. And that's a metaphor and model that I am proposing and I've used on multiple projects for looking at APIs as semi-permeable osmotic membranes. And that is the end of my talk. I'm a little early, so more time for questions.
Very insightful. I'm thinking, I'm like, I think while we're waiting for questions from the people, just join in, Laura. Like you should also. Just,
this is a stand-up comedy.
You also say osmotic, and it means that we. For me, osmotic, it's about this almost like pulling of certain things into another place, and then also accumulation. I don't know if there's like selective osmosis. Probably not.
Well, I think osmosis is selective by the fact that you have low concentration and high concentration, and that is what causes the movement across the membrane. Yes, yes. So that's the definition of osmotic. So there is movement, and it's clear where that movement will happen or should happen.
Yeah, and like what I so I love the metaphor of semi-permeable membranes, because it brings us very close to multicellular life and how cells are interacting with each other.
Yeah, I didn't think about that, but yes. So okay, I wouldn't say it was multicellular, but maybe multi-dimensional, right? Using the 3D cube as an example, you've got 6 dimensions there to account for and trade off between.
Yeah. And I think I'll just want to dig a little bit further on that. I mean, we have a question from the audience. What I'm imagining is the socio-technical system where there's humans interacting with the cube, where there's lots of cubes. Correct. And it's this, and some of the cubes are actually talking with each other directly without human interaction. Yeah. So you're getting this complex system that's built up of all these different parts. And yeah, well, I need to think more about what you described about, this layering and the filtering of the messages, and then the transforming of the messages and how they get represented. But it's very similar to what happens in biology, like when hormone that's exposed, and very, very interesting. Cool. So question from Claudia. I think she
from Greg.
It's from Greg. Okay. Do you want to say, or
I can read it too, so loudly for the recording. From Greg, a question to Don. Do you see this being generic or front-end only? That is, how do you position this with an API first approach?
Okay, so Greg, I said earlier that I want to make sure that something is validated. So I shared an experience where I've actually practically, empirically, I think that's why I titled the slide, empirical example. So I think it's generic, but it needs to be tested and validated. Just because it might make sense, and it might even seem intuitive. Osmosis is not intuitive to me. Every time I see that, it looks like magic, but it's explainable, but I have to sort of twist my brain around to make sure I adjust my model to say this is physically and physics-wise how this works. So I think it's generic, but I'd love it to be validated. And then you talk about an API-first approach. Having an API-first approach to me is like giving someone jam without bread in a sandwich. It's a layer that has to be combined with data and a few other things in order to be of value But again, I'm biased because I look at things from a human-based perspective. From a system perspective, that might be valid. I don't know if that answers your question, Greg. Please put some comments in, and I'd love to pursue this more, because I think it's generic, but I won't say that without evidence. Yeah.
We have another question from Simon, who is asking. He says, "I'm curious what inspired this approach. Which category of models did you find inadequate or lacking?"
This came from working directly in design software where everything is two-dimensional. It's planar with an infinite area, but things the systems that we're modeling are not infinite 2D areas. They're 3D, 4D, 5D in some cases, and we're still using a 2D tool to try and manage that. And one of the other things that was interesting, and hopefully you saw that in the animations, is you can take a cube, which is the same volume, the same area, but when you flatten it, it looks completely different. If you don't know that, you think you're looking at 5 different things, when what you're looking at is 5 different orientations of the same thing.
I have a connected to, because you had the composite layer where you have these formatted information blocks.
Yes.
And one thing that I actually had a talk yesterday with a startup that's building a tool that does something like that, and then exposes those those patterns. It's called Signal Pattern as a company.
Okay.
They expose those patterns as things that people that are not developers can interact with to kind of put together.
Yeah.
Because I think one thing, I think one of the things you're also kind of hinting at, I think, is that APIs per se are not necessarily, they're not really consumable for most humans. Like you have to be a developer to consume an API.
Even as a developer,
yeah, right.
You have to have a model for example, what's the sequence? Which API do you call first before the next one? Where are the dependencies? So yeah, I think that they're not consumable for a human unless you add another dimension which allows you to clearly call out and say, okay, because I'm working with a view, this is the thing that has to happen before, and that's the thing that's allowed to happen afterwards and nothing else.
And that also means that there's complex interactions between these different components.
Yes. But rather than complex, I would say they're complicated, because then there are many interactions, but they're known. The ones that aren't known are your exceptions and a few other, but at least they're in is a known unknown category, as opposed to I have no idea what this thing is doing.
It depends if there's humans that are interacting
that's
with
true.
the
That's true. Yes, you can't always predict that. So yes. So someone, I just noticed,
yes.
Greg, you said something about Parnas encapsulation. I don't actually know what that is, so I'm going to have to go and look that up. So that will be an interesting reference. And
I think that was the last one.
Yeah, Simon, you're curious what? Oh yeah, I think I've answered that one.
Just
curious about what? I think it was the pain of having to do multi-dimensional work in a 2D interface.
Yeah.
And I figured there had to be a better way.
I think one of the things I've learned exploring complexity is that it's always about, like, the models help you to gain power over what's going on.
Yes.
And different models give you different powers.
That's right. And I am completely agnostic. I will use whatever model analogy fits and works and allows me to address that. I'm definitely not an advocate for saying, okay, if this is defined in physics, which you'll see in my definitions, I can only use it in physics. That's nonsense. It describes the world And it's a way of being able to describe it, build a model, and then apply it to whatever problem that you have. So yeah, I agree with that.
And all models are ultimately wrong, but some are useful.
That's true. That's, yes. I've forgotten the person credited with that. Some all models are wrong, but some are more useful than others. So yeah, definitely. Yeah.
Very much. Another question from Greg. You seem to also take a boundary approach from like between brackets Flores, but wondered if you're aware of Apostle's law.
Yeah. So Greg, I'm already struggling to use a 2D tool to create a 3D experience. So I chose the cube because it's a universal, hopefully relatable object. And I mean, we get our stuff from Amazon in it and a bunch of other things. So it was really the simplest example to use. I was toying with, and you may have seen in the last flattening example where the T was folded into an envelope. It was still planar, but there are 3D. But that starts to get headachy unless you've had time to think about it. And I only had 30 minutes. So I chose not to tackle that today. But yeah. You're definitely right. I went for the box. But there are other options. And would love to see if there are some that you suggest.
I'm always scared because I feel that I need a philosophy degree to be able to have conversations with a lot of people in the community, because there's so much knowledge and so much.
There is, and I think we should be mixing and mixing and matching and remixing rather than trying to be original, because there's so much, I think, new even in that to discover. So yeah. So I've learned something today from Greg, and I'll definitely be looking up that what you mentioned.
Do you have a
Yes,
question?
I do want to bust in here. You mentioned the word probability, and that's one of my favorites, because the more I think about probability from a theoretical point of view, the more of this, I don't know if maybe it's just me, I get this mental vertigo where it's like, don't look down, don't look down.
Yeah.
And so you were talking about how assumptions are like determined, but you would rather use the word presumption, because that carries in it that there's probability involved in how we presume things, because we presume based on the status quo at that point.
Yes.
This is a bit of a bunny hole. Would you go down into that a bit?
Yeah, so a pet peeve of mine is when people say in a technical system, oh, I assumed this requirement. Okay, did you validate it? No. Somebody stated this the first time, and it probably was correct. But did you check it against your current variables? No, you just accepted it, that it's true, and continued until your castle that you built on sand collapses. So an assumption by definition is a statement that is taken as true without proof, which just makes me crazy. Why would you accept something without proof? We could easily test it and check it, or get somebody to test it. A presumption accepts something as true with a probability. So something can have a probability of 0, which means it's never going to happen. But you've made some validation, and then that varies depending on the conditions, what's happening in the environment that you're working in, and various other things that could happen. So that allows for a degree of change. And I think a lot of times when people talk about complexity, they're actually talking about complication and assumptions. So one of the things that I do, and I didn't bring this up here, but separately, is I have for every project that we do, we go through, we state our assumptions, we put a probability next to it of it occurring that we think is going to occur, and then we just monitor it. And, we take it down to 0 because it never happened, or If it comes up in an issue, then it's 100% at this time. What else was that based on? And therefore, what else will it affect? And get systematic to approaching risk. And one of the things that I think that affects projects and why they fail or why there's catastrophic issues is because people assume something is true without proof. So presumptions are the way to go. Put a probability against it, document your probabilities, and monitor them. They will change if something changes. So yeah.
I saw. I'm bad in remembering where I get ideas, but I read an article not too long ago where they were talking about like that probability is still assuming that its scanf is predictable. It's not fully predictable, but there's a certain probability distribution, and that in complex systems it might not even be possible to make that kind of prediction. So
that's a probability of 0.
Right.
So if you plotted it against even on a graph and said, 0.1, what is this probability? 0. Okay, it's never going to happen today.
Yeah.
Tomorrow, something may change that. 10 years ago, nobody would have thought that we'd be having visual recognition systems that we have today. So the probability then was 0. Today is 100%. What's changed in between? A bunch of stuff has changed in order to make that happen. So it's not a one and done. It's at a point in time, but you need to keep monitoring and checking it and assessing it, I think.
It's almost like assess your assumptions.
Yeah, and also the thing that I've found doing this work is if you have what I call a foundational or load-bearing assumption, and that turns out to be wrong, then you already see the cascade with everything else because you've got that structure where you've made it visible and you can assess those things. But if you're just going along and accepting, okay, it's all right, then every time that you trip or you come to a boundary or you come to an issue, then it's a symptom, but you treat it as if it's an independent thing. So that's one of my tools to try and keep up with complexity and complication, if you like.
It's load-bearing assumptions, or they become constraints, and then and then constraints to your thinking, and once those constraints are no longer true, the whole thing just falls apart, and knowing when it falls apart. Very interesting.
I hope we're going to be laughing about this 10 years later, because this is the sort of the beauty of mathematics, that all of those presumptions and assumptions are explicitly marked on the side. And if something doesn't add up, then you don't immediately assume that your model is wrong. You first look at your parameters, side parameters, like quantum theory has a history of Einstein saying this was the biggest bonkers thing that I assumed wasn't right. So let's hope we're going to laugh about this and how APIs are going to catch up with conditionals and such.
Well, or they become something else, I think. They transform into something else that just like we had assembler as the programming language of the day. I don't know about you, but I don't remember the last time I looked at assembler was 20 years ago.
Mm-hmm.
And the probability of anyone writing assembler today would probably be very, very, very low, if at all. So we need to account for conditions in the environment that change, like you said, the constraints and the variables that impact the things that we're looking at and how we solve and model those problems. So all I've done today is I've taken an approach. I applied it to a problem that I had in the space that I was working in. But I think Greg is 100% right. This could be general for anything. And I would love to get feedback from everyone to see what they've done with it. also giving credit to Brad Frost. I took a model that he made and tweaked it for my purposes. So it's a continuous evolution, I think.
I love the bringing APIs into that model. That's really, really cool. Yeah.
Can't really go around them anymore. Thank you very much.